Weather and climate often cause concern and curiosity, but understanding the facts behind the phenomena can be a challenge. We're here to help. From the University of Illinois, Urbana-Champaign, and Illinois Public Media, welcome to Weather Realness, a weekly podcast about the skies above Illinois and the world.
I'm your host, Steve Nesbitt, professor in the Department of Climate, Meteorology, and Atmospheric Sciences here at the University of Illinois, Urbana-Champaign. Lately, the weather has been changing in ways that catch everyone's attention. In media coverage, extreme weather events are increasingly linked to climate change. CBS News reports that Illinois had more tornadoes than any other state in the U.S. the last year, a trend that may be influenced by a warming climate. Across the U.S. in 2024, we saw severe weather everywhere. Hurricanes, tornado outbreaks, and massive wildfires. Globally, there were more than 600 extreme weather events, including major floods in Europe and Asia. So how do scientists figure out whether climate change actually played a role in these events, and by how much? That's where attribution science comes in. Today, we're going to talk about how that science works and what it means to say climate change influenced a storm. Speaking with us today is Ryan Shriver, a professor in the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois. Thank you for joining us, Ryan.
Yeah, thanks, Steve. Happy to be here.
So your area of research in the department is in an area we call climate risk. Can you tell us a little bit about what that is?
Yeah, from a climate perspective, climate change happens at the global scale, but the impacts are typically felt at the local scale. So what we do, or what we try to do with climate risk is understand how the changes at the global scale are going to affect or influence the likelihood of experiencing extreme events at the local scale.
So when we hear the phrase climate change influence a storm, this sounds a lot like what you just talked about. What does that actually mean?
I often get questions from the public after a big event or as you said, a big weather event, and they'll say, did climate change or global warming cause that event? So I like the fact that you use the word influence, because it's very difficult to say with any certainty whether or not climate change is causing extreme weather, because extreme weather events have occurred throughout history. But there is evidence that global warming and climate change, it could be influencing the rate of occurrence or the duration or the intensity of these extreme events, which are creating outcomes or weather events that are unprecedented or have not been seen before.
So how do scientists determine how weather is influenced by climate change and by how much?
A couple different ways. We can look at observations. We can look at the historical record and look and say or analyze, have we experienced events like this in the past? How few and far between were they? Maybe they're unprecedented. Maybe we have never seen an event like this in the past. In that case, we often turn to things like climate models, which are numerical models similar to what we use to forecast the weather. We can use the same models to forecast the weather under different types of climate regimes or different types of climate scenarios or conditions. And that allows us to set up experiments where we could look at what would this event had looked like if there was no climate change? What would this event have looked like if it happened 100 years ago before the Earth had warmed by 2.5 degrees?
So your research has looked at several different types of events and really tying it into the physical processes that drive variability in the climate system. So what are some of the key phenomena you've looked at and some of the processes that influence some of the extreme weather events you've studied?
Yeah, in our group, we look at a wide range of extreme events, starting with things like tropical cyclones and hurricanes, and all the way to tornado outbreaks, wildfires, and these things relate to weather conditions in different ways. So, for wildfires, for example, it's a very complex relationship because it's not just the weather that affects wildfires. You also have humans, you also have things that need to trigger the fire. Weather creates the conditions that can be favorable to fire. So if you have a very wet spring, for example, that leads to a lot of undergrowth or growth of vegetation near the surface, in these fire-prone areas, such as the Western United States, and then you follow that by a very dry summer where this all dries out then, and now you have a lot of fuel, undergrowth fuel that can be burned up essentially if there is a wildfire. And so that's one area where weather comes into play is just the distribution of precipitation. When you get rain, how much rain do you get? Do you get a lot of rain followed by dry conditions? This can lead to a very risky situation. In other For other perils or other weather hazards, such as tropical cyclones, oftentimes we look at what are the ocean conditions looking like. Is there a lot of excess heat in the ocean? Because this heat is what provides the fuel for these storms. So as the planet is getting warmer, the oceans are getting warmer, there's more potential, there's more fuel for these storms. All of these things are influenced and regulated by the large scale climate, and they can change or vary with climate in very complex ways. It's not as simple as just saying, oh, global warming is making all of these things worse, because there are many factors that can influence these types of climate variables that then indirectly or directly influence the weather. So it's a very tricky problem.
One of the interesting things about climate risk that's in addition to just what's going on in the atmosphere is the human dimension overlaid on that. And in terms of, for example, the wildfires that happened in California last year.
The death toll now climbing to 24 people, 8 from the Palisades fire and 16 from the Eaton fire. At least 16 people are missing, with countless injuries being reported.
Nearly 20,000 acres have been destroyed in the Palisades fire, and the fire is only 6% contained.
They were so devastating because they just happened in a place where there was just extreme exposure. So can you talk a little bit about the kind of the interplay between how climate is changing plus how society is changing, perhaps to make us more vulnerable?
Yeah, there's very complex interaction between the human and natural systems in this way. We find that the physical risk is changing due to this relationship between weather and climate, but also the human risk is changing. So from the perspective of wildfire, we see people moving into rural areas, right? So people out west in California, for example, tend to be moving out of the cities. They're moving into rural areas, and this kind of interface between the rural and urban boundary is really an area where a lot of these wildfires tend to be initiated, and that can be quite risky.
So getting into the thing you just touched on, the uncertainty, this is obviously a big deal when we're starting to make attribution studies. So you've looked a lot at this in your research. What are some of the ways that we determine how uncertain our climate projections are?
Yeah, uncertainty is a major issue, in part because our climate projections are based on climate models that we were talking about earlier. But these models are approximations of the Earth's climate system. And they're not really designed for simulating and capturing extreme weather events. They're more designed for capturing kind of global response to greenhouse gas emissions. So again, trying to connect what's happening in the global climate system to what that means for the future of extreme weather is a major challenge, and it brings in a lot of uncertainties. So we have the climate model uncertainties. We also have just the uncertainties that arise due to the natural variations of the system. Year to year, the weather changes a lot from year to year. That's outside of what's happening at the global scale. And these kind of interannual natural variations can also influence severe weather or extreme weather in ways that can overwhelm the signal that may be due to the long-term global warming trend.
So you're listening to Weather Realness, the weekly podcast about the climate and weather. We're talking to Ryan Shriver, professor in the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, Urbana-Champaign. Yeah, one of the concepts that I think, when we talk to students at the university is that, this is all what we call nonlinear, right? You've got trends in physical quantities that, you can fit a nice line to, and things are, say, like the number of tornadoes is going to increase directly with CO2. But that's not necessarily the case for a lot of reasons. One of them sort of being the fact that, as you mentioned, tornadoes are episodic and they depend on the weather, which is inherently somewhat chaotic. But we also have this concept called tipping points.
The Earth has reached its first catastrophic tipping point for human-caused climate change, according to a new report by scientists in Europe. They say warm water, coral reefs now face a long-term decline, and warn the world is also on the...
The ocean has reached record high temperatures, and 80% of the world's reefs have been affected by the worst mass bleaching event on record.
Could you talk a little bit about what a tipping point is when we talk about the climate?
Sure. Yeah, a tipping point is some threshold response in the system where you transition to a new state that is fundamentally different than your previous state. And as an example of this, you can think of sea level rise. Over the last several decades, we've had kind of this linear response in sea level rise that's largely due to the warming of the ocean. So as we heat up the ocean is a fluid. And so as you heat up the ocean, it becomes less dense and its volume increases. So as you increase the volume of the ocean, the sea level rise goes up, ever the sea levels go up. And so this is well understood kind of from a physics standpoint. And we see it. There's strong evidence of this in the observations. But what happens in the future, at least from the climate models, is that there's a non-zero chance that we may get some sort of transition to a new climate, such as through melting of an ice sheet. So if we, in addition to the linear response or the linear trend of a warming ocean, if you add in some threshold response, such as an ice sheet melts rapidly or an ice sheet disintegrates, we could have a major jump, by a meter, 2 meters of sea level rise, where we can't just simply turn back the clock. We've now moved into a new system where we've lost that ice sheet, and that would be considered a tipping point. It's a new state or a new climate state where we can't just kind of go back to where we were. We're in a fundamentally new climate system now, and that's really we call this deep uncertainty. We know that there's a chance that this could happen. We don't have a good understanding of when or how it may happen because these processes are very difficult to model in climate models, but there's observational evidence that it's happened in the past through our geologic records. This is what controls glacial, interglacial cycles. So we do know that these things happen they happen naturally on long 10,000 year timescales. But what we're doing now is kind of an uncontrolled experiment where we say, let's just put a bunch of carbon dioxide into the atmosphere and see what happens to the planet. And we really don't have an analog for this going back in time, at least not in the last million years.
Right. So coming back to sort of what we know and what we don't know, in terms of attributing different phenomenon, you hear in the media, this hurricane that hit Florida was X% stronger, et cetera. What can attribution science say today with pretty high confidence?
Oh, that's a good question. Yeah, I would say with high confidence, I think storms are getting wetter. There's more rain. Okay, again, because as the planet warms, as the atmosphere warms, it holds more water. Okay, so this is again kind of well known from the physics perspective. This is not even climate science, but as you increase the temperature of a gas, it will hold more water vapor. And that's what we're finding in the atmosphere. And so when we have a storm, such as a tropical cyclone or a severe convective storm, it's producing more rain. And I would say this is probably the biggest fingerprint of global warming on extreme events that we have right now. There's some other things that can be debated, whether storms are getting bigger, are they becoming more frequent, are they moving more slowly? There's evidence to suggest all of these things, but again, because of the natural variability in these physical processes and year-to-year variations, it's very difficult to tie it to global warming. But in terms of rain production, warmer atmosphere, more water.
Yeah, so that's something we hear, in the media. It's hard to, as scientists, to hear some of the things that they say. And there are other efforts. For example, I know there's an effort to simulate hurricanes in near real time and actually
Yeah.
try to compare the climate change influence on the speed, the intensity, the strength of the wind. And they can run these things almost in near real time and report to the media right after the event. Um, do we need to be a little bit more cautious about hurricanes?
I think so. And this is just my personal opinion, but that type of analysis is quite useful, but at the same time it's somewhat anecdotal in the sense that you're looking at one specific event. I think if we really want to get to the bottom of the effect of climate change on extremes, we have to have a more systematic approach or come up with a more systematic approach that can collectively account for all of these different types of changes or all of the physical processes and not just for one storm, but for everything. Again, because there's so much variability from one year to the next, especially with hurricanes. You might have a really bad hurricane year followed by a year where there's almost no hurricanes, or or you may have a year where there's a lot of hurricanes, but they're not making landfall, right? So does that mean it was a not a bad hurricane year, or did we just get lucky in the sense that they didn't make landfall? Right. So there's a lot of uncertainty and nuances, I guess, complexities within these types of storms and systems that make it difficult to kind of disentangle what are the most physical factors or most important physical factors.
So, Ryan, what are some misconceptions you encounter when people try to link climate change and extreme weather?
I think the biggest misconception or some of the misconceptions that I run into is being able to separate weather from climate. Okay, so weather is again what's happening outside your window. It's short-term events, small-scale events. Climate is what's happening on the global scale, and it's how the system is changing over long periods of time. Okay, so you can almost think of climate as being the average of the weather. Right. So one misconception that I get is you have one cold winter, a really cold winter, such as this past winter. February was pretty cold, and then people will say, "Hey, what happened to global warming? I thought the planet was warming. Why is it so cold right now?" And you wonder, but we're not looking at the planet, right? We're looking at the weather outside of our window, and it might be cold here, but it might also be warm somewhere else. And so, if you really want to get an idea of what the climate looks like, we need to either average everything spatially over the entire planet, or we need to look at kind of long-term trends of what's happening with the weather outside your window. If I wanted to take the temperature of the planet, I wouldn't just put a thermometer outside my front door and say, here's what the climate looks like. I would need to have good coverage of the entire planet in order if I wanted to really have an estimate of what the temperature of the planet looks like. I think that's the big difference, is separating out weather from climate.
Yeah, one of the challenges here, of course, is especially a lot of the eastern two-thirds of the United States is covered by a warming hole, so to speak, where we have not seen as much warming as other parts of the world. And so when we talk amongst ourselves as Americans, we haven't seen the amount of warming that other places have seen. And so that really speaks to your point about putting a thermometer outside of our window here in Illinois. It doesn't seem like the climate has changed, even though it has actually changed dramatically if you look at things like the length of the winter season and the number of extremely cold days.
That's right.
They're really on a sharp decline. And so can you talk a little bit about some other changes that you've seen in extreme weather events over time?
In terms of changes in extremes, kind of relating it back to the work that is done in my group, we see robust changes in wildfire, right? Whether it's the amount of area burned, the number of fires, the duration of the fire season, those things are all changing. And I say this not from like a year to year perspective, but on a long term, multi decadal changes. So these are definite climate signals. From a severe convective storm perspective, we see lengthening of the tornado season. We're seeing tornado outbreaks during times of the year that we didn't normally used to see tornado outbreaks. We're seeing shifts in where tornadoes are occurring, more towards the southeast, more towards the winter months. So again, these are long-term changes that are more attributable to global warming or to climate than to any sort of kind of random variability within the system.
Yeah, and of course, the place where nobody really lives, and we don't really think about it too much here in Illinois, is the ocean. How do changes in the ocean actually physically influence extreme weather events that we see here on land?
Yeah, they have a big impact. So the ocean is a huge reservoir. It's a very large heat capacity. So the ocean can hold a lot of heat. And if you talk to an oceanographer, a lot of them would say global warming is ocean warming because the ocean has a much larger heat capacity than the atmosphere or the land. So, and it provides a lot of the fuel, the heat that it goes into forming and maintaining these storms, such as hurricanes and tropical cyclones. It can also influence the strength and position of the jet stream, which carries along weather systems within the mid latitudes. It can also influence natural variability, such as El Nino, La Nina cycles. This has important implications again for the jet stream and for precipitation events, floods versus droughts. Yeah, it can play a major role, and it also has an important role in regulating sea level, contributing to sea level, and also to contributing to land ice, whether it's ice sheets melting or ice sheets forming. It's very closely connected to ocean conditions.
Yeah, a lot of times I think when I talk in the public and they ask me, like, what do you think this winter is going to be like, for example, and I start talking about the ocean, and I think people are like, how could it possibly have an impact here in the middle of North America? But it turns out that it's very dramatic.
Yeah, that's right. Particularly what happens in the tropical ocean, because it can influence atmospheric waves. And atmospheric waves are what carry the weather around. And these things, what's happening in the central Pacific Ocean, for example, can influence the weather that's happening here in the Midwest. This is why, when we, again, connecting what's happening at the global scale to what's happening outside of our window, you really do need to have a good representation of what's happening on the entire, around the entire planet if we want to have a good understanding of what's influencing the extremes here locally. Absolutely.
Well, Ryan, it's been a pleasure. Thank you for joining us.
Yeah, thanks, Steve. It was great being here. Great talking to you.
Ryan Shriver is a professor in the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, Urbana-Champaign. For those just tuning in, you're listening to Weather Realness, the podcast about weather and climate. I'm Steve Nesbitt. Have a weather or climate question you want us to tackle? Leave us a voicemail at 217-333-2141 or email weatherrealness@illinois.edu.
Weather Realness is produced by
Jeff Frame,
Trent Ford,
Steve Nesbitt,
Reginald Hardwick,
Stephanie Orellana, and myself, Maddie Stover. Funding for this podcast is partially provided by the Backlund Charitable Trust. Weather Realness is produced by the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, Urbana-Champaign, and Illinois Public Media. We'll talk with you again next week.